So you have to design a flat bed drive for a fan which is running at 360 rpm, which is driven by a 12 kilowatt 1440 rpm motor. Okay, the belt drive is open type and the sender distance is 2 meters. So we have to design a flat belt drive. That means we have to find all the parameter. Okay, now let's look at the solution part. So the RPM of driven is 360 RPM. That's a fan here. Then the power is 12 kilowatt and the RPM of driver is 1440. And sender distance is 2 meter. That's also given. So we have the service factor CS value which is not given in the question. Even though it is not given, you have to assume as 1.2. That's the another value. If not given, the value that we'll be assuming is 1.2. Okay, suppose if some value is given, you have to take that. Okay, then even though we have given a power value 12 kilowatt, we cannot take that value for solving the problem. We have to use design power. That's the value we need. Not to find design power, we have to multiply the service factor with the given power. Okay, so the design power PD will be 14.4 kilowatt. Next is we have to first thing we have to find in this type of round. First thing we have to find is to determine the diameter of the driver pulley. Okay, that is taken as small d. Okay, we have to find the diameter of the driver pulley. Okay, not driven, it's driver. In this case, that's the motor. Okay, so that is found by the equation 630 into cube root of PD by W max. W max, that maximum angular velocity, can be found out by the equation 2 pi n by 60. That n, that should be the RPM of the driver. Okay, so substituting, you will get the value of diameter as 290 mm, but you cannot take the value 290 mm. As you know, you can only proceed with the standard size of a diameter. So from the standard table in the data book, next standard value will be 315 mm. So that's the standard diameter of the driver pulley. Next, we have to determine the diameter of the driven pulley. That can be found out by the equation 1 minus epsilon into d into I. So this epsilon is what is slip. It's a slip factor or slip. So it's usually given the question, even though it's not given, you have to assume it to be 2% of slip. So epsilon is equal to 2%. Okay, while converting into removing percentage, that will be 2 by 100. And the small d, you already know that's the diameter of the driver. And I is the, we know that's velocity RPM ratio or diameter ratio. It's always driver by driven. Okay, that will be 4. So now you can find the diameter of the driven pulley, capital DS. By substituting, you will get this 1234.8. Even though that's the value we get, we cannot actually know. We cannot take that value. We can only take the next standard value. That will be 1250 mm. Okay. So as next thing we have to find is the belt speed. Okay, belt speed is small v. That is can find by this equation pi dn, not simply pi dn by 60, pi dn by 60 into 1 minus epsilon. We know epsilon is slip, that is 0.02. And small d is the diameter of the, you know, driver, and so obviously that RPMs also will be of driver. So you will get the belt speed in meter per second. Okay, so one thing you have to check is that the belt speed should be in meter per second. In order to that, this diameter, we know that we get the answer in mm, so you have to convert into meter. That is why there is a 10 raised to minus 3 put here. That is because of the conversion of mm to meter, because we need the belt speed in meter per second. Next is coefficient of friction. This equation is also in the data book. So that v is the belt speed, which is just find out. Substituting the coefficient of friction value will be 0.51 m. Okay, 0.51 will be the coefficient of friction. So next we have to find the length of the open belt. Since this is an open belt, they have already mentioned, we have to take this equation specifically from the data book. There is equation for both the closed belt and open belt. We have to take the equation of open belt. So we know all the value at C is the center distance. We have given the value in meter, but you have to convert it into mm before substituting in the equation. All other value, you know, capital D and small d, the diameter of the driven and driver, you know that. So you get the value length of the open belt as 6.56 meter. Next is we have to find the angle of contact. That is this equation is also in the data book. We know all the value capital D, small d, C. Only difference between this equation is the difference sign at these 2 points. So the smaller pulley, angular contact of small pulley and angular contact of the larger pulley is 2.61 radian and 3.6 radian. Next, we have to determine the width of the belt. So in order to find width of the belt, we'll be using this equation. If we look at this equation, you see the value of mu theta. Okay, there is 2 mu theta. Mu is common for both small pulley and larger pulley, but theta, there is theta value for smaller pulley and theta value for larger pulley. So what we do is we find the value of mu s into theta s and mu s into theta l. I mean, for both smaller and larger, we find the value. And when these two value, we take the smaller one. Okay, the smaller one will be 1.361, and that will be used in this equation. Okay, all other value we know. Another thing we have to assume is the design stress sigma d. If it is not given the question, just assume this flat belt is made of leather and the value to be 2 megapascal. You can assume any value because it's not given. So generally this design stress will be taken in 2 megapascal. So take this value. Then another thing we have to assume the density of the leather is 1000 kilogram per meter cube. So speaking of that, you should know this equation. Okay, the weight is actually the weight W is equal to rho g. So I can rearrange this rho as W by G. As you can see in this equation, it's already having W by G, right? So already have W by G. So this W by G can be replaced by rho. That means the density of the flat belt. Okay, assuming to be leather, that will be 1000 kilogram per meter cube. Even if it's not given, just assume this value in all this type of problem. So I can replace that rho by W by W by G by rho. Okay, so all other things you have to substitute. You know the value of PD, design stress, all other parameters you have substitute, and you get the value of BT as 576 mm square. Okay, so next we have to determine the thickness. So thickness is given by the relation 0.02 into D. D is already on now the diameter of the driver. So thickness will be approximately 6 mm. You know the value BT. From there you can find the value of B. It's 96 mm. So in standard table also the B value, but value is all it's already 96 mm. So no need of change. The calculated value and standard value is same. Okay. So we get the width as that width as 96 mm. The last thing in design problems you have to determine the tension. Okay, so tension is we have solved it by using a couple of equations. We will find we'll be solving it by taking a couple of equations. First, that this equation you can find in the data book. Design stress equal to T1 minus T2 into V by 1000. Okay, from that you can find the value of T1 minus T2. That will be one equation. Then this is our equation is also present in the data book. T1 minus Tc by T2 minus Tc into equal to e raised to mu theta. That Tc can be found out by this equation. Here also as W by G can be replaced by rho, which you know the value is 1000. So DC value, you got the value of Tc. Substituting in this equation, T1 minus Tc whole divided by T2 minus Tc equal to e raised to mu theta. You will get the value. I mean, there is we got another relation between T1 and T2. Okay, so we have a linear equation, two linear equation having variable T1 and T2. Solving this equation, we get the value of T1 and T2. Okay, so now we got the tension. Now we already got the tension and the flat. The last thing we have to find the initial tension value. It is termed as T0. This equation is in the data book. So you can use this equation. You already know the value T1 and T2 to find the value T0. But by substituting and solving the T0 value, the initial tension value will be 804.95 Newton.